Thank you very much, and good morning or good afternoon. What I'd like to talk about is the James Webb Space Telescope, NASA's successor to Hubble. But before I do, I wanted to give you a recent history of astronomy from a personal perspective. I'll do a couple of charts on that, and then we'll get into the mission itself. I'll talk about the challenges and the status of this mission, and then I'll sum up. And as far as doing it from a personal perspective, I thought I'd tell you what astronomy was like when I was a high schooler, and that was in the year 1976. So I took one of my old textbooks from 1970s, and here were the fun facts of astronomy back then. First, our solar system was thought to contain 9 planets, and it had 31 moons that were only observed, even with the biggest telescopes in the world, as points of light. That's all they were. You could see the 4 moons of Jupiter. The really big telescopes could see all the other moons, but it's really just specks of light. The only star that was known to have planets was the Sun. A lot of astronomers suspected there were other planets around other stars, but none was ever really detected. Some astronomers were actually seriously debating as to whether our solar system was a fluke, whether we were the only ones that actually had planets. Of course, science fiction writers of the day didn't want to hear that, and Captain Kirk still traveled to all these stars and visited all these other worlds. The stars could only be observed as unresolved dots of light. Even in the biggest telescopes in the world, you could not see the surface of a star for a lot of reasons, one of which was looking from the bottom, looking up through the atmosphere means you're looking through an ocean of air, and the air distorts the images. The universe was known to be expanding, but most astronomers believed that the expansion was slowing down, might actually stop and reverse. And the reason for this was almost common sense. When you throw a ball in the air and it's acting in gravity, eventually it stops and comes back down. And they thought that the gravity of the whole universe would end up stopping this expansion and crunching it down. But also, the farthest object detected in the universe at that time was so far away, its light was traveling 5 billion years to get to us. So it would be at least 5 billion light years away. It was actually a little more than that. And the universe was thought to be between 5 and 10 billion years old, which was a problem. It was a big problem in my day because some of the oldest stars in the universe, we had very good reason to believe, were 13 billion years old. It's hard to have a star older than the universe was. And finally, the content of the universe was thought to be pretty much commonly known. We thought all the matter in the universe consisted of protons, neutrons, and electrons, and that all the energy in the universe could take one of 4 forms, or one of 4 forces: gravity, electromagnetism, nuclear, or the strong force, and what's called a weak force, and that's the thing that kind of controls the way some atoms break down, called radioactivity. At any rate, this is what the textbook said in 1976. Since that time, today, there are 8 planets in the solar system. We lost one. And there are 178 other planets. Which one did we lose? Pluto. Well, poor Pluto is now characterized as a dwarf planet. However, whereas we lost one planet, we gained 4 other dwarf planets. And they're shown here, at least as artist renditions. One of them, Eris, is pretty much just about as big as Pluto. And by the way, there are about 4 other candidates on the books that they're still investigating. And as for moons, there are currently 173 planetary moons. And this changes almost by the month, but I took this off of Wikipedia a couple days ago. And these are no longer just specks of light. These are imaged worlds. We've imaged them, we've sent spacecraft to them, we've mapped them. One we've even landed on. That's Saturn's moon Titan, which is shown down here. One of the only moons in the solar system known to have an atmosphere. Next. Whereas back in my day, there were no other solar systems known for sure except our own, we now know there are at least 687 confirmed planets around other stars. We call them exoplanets. And by the end of this year, that's probably going to be between 2,000 and 3,000. They were discovered in a number of different ways, but the most exciting came in about 2008 when one of my colleagues at NASA and his team announced they had actually photographed or imaged a planet around the star Fomalhaut. Fomalhaut is a star. You can see it very low on the horizon from here in the fall. It's about 22 light years away. Around Fomalhaut is a disk of debris, dust and asteroids. And we're using the Hubble Space Telescope and an instrument called a coronagraph. They subtract out the light from the star itself, which would overwhelm the planet. The planet would be about a billionth of that light. The coronagraph subtracts out that light, and what they found was a little dot up here, right there, Fomalhaut B. And I tried to get a better picture, but over the course, since they've discovered that, you can see the planet actually orbiting the star. Now, in addition to that, one of the more common ways of doing this, we're discovering planets in droves these days through a technique called exoplanet transiting. What happens is a lot of these planets end up eclipsing their parent star. And if you just measure the brightness, every once in a while you can see a dip like that. It's a very small dip, but it's measurable. You can get the size of the planet from the shape of that dip. You can get where its orbit is from the duration of the dip. And there's a telescope out in space now called Kepler that has discovered, I think they've announced 300 planets from Kepler. And by the end of this year, they'll think that's going to be over 2,000. So whereas in my day, planets were thought to be rare, we now are beginning to believe most stars, if not all of them, have planets. Back in the day when I said we couldn't see the surface of stars, well, today we can see their surfaces, at least of the bigger ones. This is a star, Betelgeuse. It's in the constellation Orion, and we photographed it. Here are images of Betelgeuse in different wavelengths of light, but you can actually start to see surface features. These are bright spots, and had I found better pictures, you can actually see star spots on these. One of the other things that's very exciting, at least it's something I'd like to pursue, we can also begin to X-ray the stars and figure out what is actually going on inside of them. This was unheard of when I was in high school. But by measuring very small, minute changes in their brightness and their size, we can start to see the way these stars pulsate or ring, just like when you ring a bell. The way these stars ring tells us something about their interior. By the way, it's the same technique that's used by geologists to figure out what's in the Earth. Every time there's an earthquake and the Earth shakes a little, those waves go through the Earth, and by receiving those waves at different points, you get to know what's inside. In the same way, we now know what's inside of these stars, and we can tell a lot about them, one of which is their detailed composition, which tells us about their age, which helped us out in one of our problems. We now believe, using some of these techniques, that the oldest stars in our galaxy are probably 12 billion years old. That's going to be important in a second. Okay, now let's talk about the universe at large. It was recently announced that an object has been detected in a Hubble photograph that is about who's so far away, its light has been traveling to us 13.1 billion years. And the interesting thing is, the deeper we look into space, the more stuff we see. We haven't seen the end yet. And that's kind of exciting to a lot of us. Measurements, and this is a very big deal. A group of scientists just won the Nobel Prize for this. Whereas we used to think the expansion of the universe was slowing down, we find out it's accelerating. And gravity shouldn't do that, not a form of gravity that we know it, which led scientists to believe that there's something else at work that has been termed dark energy. There's some kind of energy that is providing that acceleration. Now, because the universe is accelerating, that means it was probably going slower in the past. And if it was going slower in the past, that means the universe is probably older than we thought. We now believe the universe is 13.7 billion years old, which is neat because now it's older than the oldest stars that we see, which are 12 billion. Things started coming together. And finally, when cosmologists, astronomers who study the universe as a whole, start tallying up all the stuff of the universe, they find the stuff, most of it is not ordinary protons, neutrons, and electrons, bosonic type matter. That accounts, normal matter accounts for only 4% of the universe. 22% of it is dark matter, matter that just doesn't seem to behave like normal protons and neutrons, yet its gravity can be detected by its effect on other galaxies. And then almost 73%, 74% is this dark energy. So right now, read an astronomy book today, and the bottom line is we don't know what 96% of the universe is made of. That's both discouraging and exciting because it gives people like me work. Let's talk a little about telescopes too. Back in the day, in the 1970s, the biggest telescope, the biggest practical telescope on Earth was Mount Palomar. And today, the biggest telescope that's in use right now is Keck. Mount Palomar has a mirror that's 5 meters across. These are shown to scale. The Keck telescope in Hawaii has one that's 10 meters across, and it's made in a different manner. It's not one big, humongous lump of glass polished to a parabola. It's 36 individual 1-meter segments, each polished to a certain shape, and each individually aligned such that when they add up, it gives you a 10-meter parabola. So it gives you one single parabola that's almost twice the size of Mount Palomar. This has a lot of advantages, by the way. If one mirror breaks, you don't have to change the whole mirror. You change the one segment. And it also gives you some way to tune them. If anything were to get wrong with this mirror, you'd have to replace it. Here, you just replace that individual segment that needs to be replaced. It was in the early 1960s and 70s that astronomers started realizing that, hey, we should be putting telescopes in orbit, and they put a couple small telescopes into outer space. And the reason for this is, there are a couple good reasons for it. First, when you observe on the ground, as I said before, you're looking up through an ocean of air that's approximately 70 to 100 kilometers tall. That ocean of air does a couple bad things. First, the starlight that comes in it gets reduced quite a bit. The atmosphere absorbs it, scatters it, and at some wavelengths, the atmosphere allows no light through at all. One of those wavelengths is in the infrared, and I'll talk some more about that in a little bit. Also, the atmosphere itself glows. Some of the light is scattered from the ground. Other light from the atmosphere is that it's just hot and it's glowing. So it's throwing all this extra light that comes in as stray light or noise, and it makes what you're looking at that much harder to see. In addition, the atmosphere is not static. It moves, and sometimes it moves turbulently. Turbulent meaning little currents or eddies or swirls. And those swirls at the top of the atmosphere can give astronomers a problem. If you take two stars that are very close together, and the light from those stars is coming in straight and true, all these waves or ripples in our atmosphere can send them on different paths and blur them, so that when you see them at the telescope, you can't always distinguish two stars as two. Instead, they look jumbled. They might even look like one star. And generally, the smallest angle that you can see through the atmosphere is about 1 arcsecond. And if you want to know what 1 arcsecond looks like, take a penny and put it about 2¼ miles away. That's the angle of 1 arcsecond. To put that in perspective, I showed you a picture of Betelgeuse a little while ago. Betelgeuse is about 0.04 arcseconds. So when you think back, why did the astronomy book say you'll never see a star? Because the best you could see is 1 arcsecond, and these stars, the big ones, were less than a couple hundredths. Finally, if you want to know what this stuff does, there's another effect that you see with your eye, and that's it makes the stars twinkle. And observing from outer space solves all these problems. So in the late 70s, 80s, and in the early 90s, NASA started to put up a fleet of observatories that they called great observatories. And these looked at the universe in all the different parts of the electromagnetic spectrum: gamma rays, X-rays, ultraviolet, visible, and infrared. And the most popular of these was the Hubble Space Telescope. It was launched on the space shuttle in April of '90, and it's still working after 5 servicing missions. It orbits the Earth at about 600 kilometers up. It has a mass of 11,600 kilograms. The primary mirror's diameter is 2.4 meters, about half of Mount Palomar, but because it's above the atmosphere, it does much better. It looks at wavelengths in the ultraviolet and in the near-infrared. And so far, Hubble has hosted 11 different instruments over its 21-year life, because over these 21 years, astronauts have replaced them. and the data output is 27 gigabits. I won't dwell on that too much. Hubble is expected, its orbit's going to last at least another 20 years, but chances are the parts on it may start to go. However, we think there's another good 5 to 10 years of Hubble life still there. Okay, so that's a snapshot of it, what astronomy was when I was in high school and what it is today. So now we'll start talking about the James Webb Space Telescope and what we want it to be in the future. In the early 90s, almost the time Hubble got up there and about the time we fixed Hubble's problem, astronomers started to convene and say, what do we want the next space telescope to do? And they came up with four themes that they wanted it to address. First, they wanted to see the first stars that turned on in the universe. Today, when astronomers look at how stars are made in our galaxy, they think they have a handle on it. But one of the key things they need to make a star is dust. Dust helps make stars. But in the very early universe, there was no dust. In fact, most astronomers will tell you dust ends up coming from stars. So there is a little bit of a problem right now. How were the first stars made? So let's see if we can find them and see what they look like. The next, let's see how galaxies actually came to be what we are, be what they look like today. Today, the average galaxy looks a little like that. You've seen pictures of it. But when we look at the very early galaxies, those that are about 13 billion light years away, we don't see that kind of thing. We see almost irregular type of smudges. So somewhere between 13 billion and today, galaxies changed and evolved and took on these shapes, and we want to see how. The next thing we'd like to see more and learn about how stars in our own galaxy, the ones that are near us, are actually being born. And finally, when this first came out, they said, hey, we want to learn more about planetary systems, so let's look in our own solar system. But as I told you recently, we found other solar systems, so now we'll explore those other planets with James Webb. That's what they want James Webb to do, so now let's start designing it. Well, if you're going to be looking at stuff that's so far away that it's farther away than 13 billion light years, it's going to be very, very dim. Matter of fact, it's going to be between 1 and 10 nanojanskis. Well, what does that mean? Well, I have the number up there. But about 10 nanojanskis is how bright a child's nightlight would be. And a child's nightlight is about 5 to 7 watts. Put that on the moon and try to see that from the Earth. That's how bright these things are going to be. Well, if you're going to try to see something that dim, you need something that gathers a lot of light. And what we calculated was James Webb had to be at least 6 meters across. And 6 meters across is roughly, I'll say from there to about there, maybe a little, that's probably about right. 6 meters across and 25 square meters of an area. Well, even at this size, the telescope will only collect one particle of light, one photon from these things every second. To put that in perspective, when you go outside at night and you look at a typical very bright star like Vega, your little eye, about that big in diameter, is collecting 1 million photons every second. And the other problem with this is, even though we're going to put James Webb in outer space, it's still immersed in our solar system. Our solar system has dust, and that dust actually glows. And what we're finding is that dust will be dumping 3 photons per second into James Webb. So the background will still be brighter than the stuff we're looking at. In order to get this to work, we're going to have to look for these dim sources and stare at them for days, maybe 10 days, to get a good signal. Okay, so we needed something that's 6 meters in diameter. We need a big telescope. What wavelength should we look at? Well, one of the things James Webb wants to do is see the first stars. Well, when a star is born, it's typically very hot. And when it's very hot, that means it's going to be emitting photons, it's going to be emitting light that's blue or ultraviolet. But these photons are going to travel across the universe for at least 13 billion years. Now, they're going to be traveling through a universe that is expanding for 13 billion years, and by the time those photons get to us, they would have stretched out with the space they're traveling through, and instead of being ultraviolet photons, their wavelength will instead look like infrared. So if we want to see those first stars, we need a telescope that works not in the visible, where our eyes work, but in the infrared. Typically something around 0.6 to 5 microns. And by the way, the light that you're used to seeing is about 0.7 or 0.5 to 0.7 microns. We also want to see the new stars that are being born in our own galaxy, and what I told you earlier was for a star to be born, it needs dust. Stars are born in cocoons of dust, and that means we can't see them being born. Visible light can't penetrate the dust, but infrared light goes through dust like X-rays. This is a famous photo of a nebula called M16. You can see these pillars of dust, and in these pillars, new stars are being born, but we can't see them. However, take that same picture in the infrared, and you can see right through those pillars. So if we want to see these stars being born in their dust cocoons, look in the infrared. Best one is 5 to 28 microns. Bottom line is, JWST is going to be an infrared telescope, not a visible. Well, if you're going to make an infrared, you need the type of cameras and detectors that work in the infrared. We've selected 4 specific instruments: the near-infrared camera, a near-infrared spectroscope, a tunable filter and fine guidance sensor, and a mid-infrared instrument to actually detect this light. Okay, well, James Webb has to be big, 6 meters. It has to be infrared. The trouble with making a telescope infrared is that things tend to glow in the infrared, especially if they are temperatures like you and me. This room right now, and your bodies that are around 300 degrees Kelvin or so, are glowing. Ask any soldier who uses a night goggle. He can see you in the dark because he's watching you glow in the infrared. We don't want this telescope to glow hotter or brighter than the stuff we're seeing. It would overwhelm the signal. Well, that means we have to make it cold. And the James Webb telescope and its cameras have to be colder than 50 degrees Kelvin. That's minus 369 degrees Fahrenheit. Well, you want to make a 6-meter telescope that's going to weigh, with its instruments, around 4,000 kilograms, that cold. You're not going to build a refrigerator that big. The way to do it is let it cool down passively. Expose it to deep space and let it just cool down. Well, to do that, we got to get it away from the Earth. The Earth glows at 300 degrees Kelvin, and we got to shield it from the sun. So, first, James Webb will not be orbiting the Earth like Hubble. We are going to put it 1.5 million kilometers away, or that's about 1 million miles away. It's going to be out beyond the moon. It's going to be at a stable point called the Lagrangian point, second Lagrangian point. It's about 1 million miles away from the Earth on the opposite side of the sun, and it will orbit around the sun at the same pace that the Earth orbits around the sun. This has another advantage. The sun, the Earth, and the moon will always be on the same side of that observatory. So the next thing we got to do is build an umbrella that makes sure that sunlight doesn't get to the telescope. And the good thing, having the sun, Earth, and moon on the same side all the time means that umbrella is going to work on all 3. And that's what we're going to do. So, I've just walked you through the major designs. This is what we come up with. The James Webb Space Telescope will have the dimensions about the size of a tennis court. Here's the sun shield. It's about 21 meters long, about almost 15 meters wide. Here's the 6-meter telescope. And like Keck, we're not going to build a 6-meter lump of glass. We're going to build 18 individual pieces of glass that we can tune and move individually. 18 individual segments. And furthermore, the hot part of the observatory, the electronics, the radio transmitters, the solar rays that turn sunlight into electricity, we'll put them on the hot side here. Now, most launch vehicles cannot fit something the size of a tennis court on them. So after we build this beautiful telescope and align it and prove it works, we fold it up and discombuberate it and do what no other telescope maker would ever dream of. And we got to fold it up to look like that. And I'm going to show you how this unfolds in a minute. Well, just to give you a sense of scale, that's a full-scale model of the telescope. And there's Mrs. Menzel's baby boy. That's me, right about there. Here are the parts of the observatory. First, the telescope parts there, and I'll describe them a little better in just a second. The cameras are going to go in the back here. That's where those 4 cameras, 4 instruments are going to go. Here you see the sun shield that consists of 5 individual layers. What happens is whatever sunlight leaks through the first layer gets trapped here and squirts out that way. And whatever gets through there gets trapped again and squirts out that way. So that only about a watt or 2 of actual solar energy will make it through. And finally, there's the normal spacecraft bus with the radio transmitters, the power, the propulsion, all that kind of thing. How does the telescope work? Well, the telescope works by using 4 mirrors. Starlight comes in and bounces off that big mirror called the primary. It gets sent down to the secondary and coming to almost a focus. The secondary mirror bounces it down to a 3rd mirror right here, which bounces it to a flat mirror, and that flat mirror can actually move. It's called a fine steering mirror. That'll help us correct some of the pointing errors. And then it'll send it down to the cameras here. Okay, so we've designed the telescope, we've designed the observatory, we know what that's like. Now, my primary job as a systems engineer is to do all the rest. So what do we got to do? First, we need a ground system that can control the telescope and talk to it. Well, we already got one. The Space Telescope Science Institute, the ground segment that controls Hubble, will use that same one. We'll use the Deep Space Network at JPL to control it. We got to put it into space now. How do we do that? Well, we have partnered with the European Space Agency, and they're going to provide a French launch vehicle, the Ariane 5, shown here. It's a good deal for everybody. The Ariane 5 is about $250 million, $250 million. Europe is donating it, and in return, we say, hey, we'll give you 2 instruments you can fly on this telescope. So it's a win-win for everybody. The Ariane will launch us into a direct path out to the L2. As we go out, we'll separate from the launch vehicle, we'll start to deploy, we'll keep in constant contact through a period of about 60 days or so while we deploy the observatory, unfurl it, and check it out. And then after about a 100-day cruise, we settle into a nice stable orbit around the L2 point, and we begin the work of getting our science data. So I want to show you, I have a video now, God willing it'll work, of what the Ariane launch will look like. So if you, Phil, if you could hit it. I took 4 years of Latin in high school, only to go to Paris 9 or 10 times and not speak a lick of French. I guess the sound is not working. Oh. And you got to, let's see. Okay, here we go. This was a launch of a satellite, Herschel-Planck, that is going to the same point as James Webb. The umbilical separates, the engines fire, but you ain't lifting off until those big solid rockets on the side, similar to the space shuttle rockets. And there we go. Now, I've seen 2 space shuttle launches, and it's really impressive when you see those solid rockets, even from a distance. By the way, if you've ever been to a shuttle launch, by the time the sound hits you, the shuttle is already so far up, it's unbelievable. You'll see most people go outside to watch the launch, and right about now, the rocket's getting so far away, it's not really all that impressive. And that's where they start coming back into the control room to see what's going on here. Those solid rockets burn for about 2 minutes. And then the other parts of the rocket burn for another, I'd say about 5 minutes. And we'll see there's actually, now we put movie cameras on the rockets themselves, So we'll be able to see the solid rockets come off in just about a second. And I really should have taken French because I got to know what these people are saying to themselves when they launch my satellite. And did we? Oh, here comes the sound. Which it did. And that's what the separation looks like. Okay, let's. Nope, I don't want to do that. Can you, oh, move the cursor. I want to go to the next one. Okay, now move the cursor back on. Now that we've launched James Webb into space, we'll deploy it. The solar array comes out, the high gain antenna. Here's the sun shield. Now those protective covers are unfurling over the sun shield. And now we'll very slowly start to unfurl the sun shield. By the way, just to give you some perspective on this, that Ariane rocket will put James Webb farther than the moon in about 10 hours. We'll start deploying the sun shield at about 2 days. We'll do it very slow, making sure nothing gets tangled up very carefully. And after we've deployed it out, we start tensioning the 5 individual layers. And it's a little hard to see, but you'll see the 5 layers start to separate from each other. And at around 2 or 3 days into the mission, we start to deploy the telescope. The secondary mirror will be the first thing that swings down, and then the 2 wings come out. By the way, you can see now why we had no choice but to make the mirror segmented, because to fold up and put it in the launch vehicle, we'd have to break it somewhere. Okay, and if you could just move it out, I'll go to the next slide. No, don't want to do that. Okay, there we go. Okay, so we've designed the James Webb. Let's talk about what's hard about this, because there are a lot of things new about James Webb that are difficult. First, let's compare it to Hubble for a moment. Well, I have the 2 pictures, and they are to scale. There's the James Webb, there's Hubble. There's our mirror, 6 meters, and there's the Hubble mirror, 2.5 meters across. And here's a table that sums up the major properties of each, but I want to highlight to you a couple of the things that make my life interesting. First, NASA has told me and my team, well, you got to have 5 times the collecting area of Hubble. We've already explained why. But you got to be half the mass of Hubble, which really isn't that surprising. Hubble orbits 600 kilometers up. We want to go 1.5 million kilometers higher. It takes more oomph. The launch vehicle to do that can't carry as much mass. So because of the launcher, we have to keep the mass under 6,500 kilograms. Then the other big deal, we got to make James Webb cryogenic. The Hubble Space Telescope, at least most of it, operates at the same temperature that you or I are at right now. But James Webb has to operate at 40 Kelvin. And there's a lot of interesting things that happen when you try to make something work at 40 Kelvin. For instance, the mirrors, and just materials in general, when you cool something that has a nice shape at ambient to 40 Kelvin, it'll warp, it'll distort, it'll bend, it'll change. And that happens to the very mirrors that we're polishing. So what we have to do for James Webb is polish the mirrors such that they're distorted at ambient temperatures by the right amount, such that when we cool them down, they'll undistort and be the right shape at 40 or 50 Kelvin. That's called cryogenic figuring, and that is a very intricate, hard process. It involves a lot of trial and error. Polish the mirror, take it down to cryogenic temperatures, see where the errors are, and then unpolish those errors back at ambient, cool it down. It's a long process, and it's a hard one. Well, the other challenge that I've showed you is we have to take a perfectly good telescope, and after we align it and make it, discombobulate it. Well, that means that once we put this thing on orbit and we do all those deployments I just showed you, we need a way to align it robotically or remotely from the Earth. When we deploy it, all those segments are going to be mispointed. The secondary mirror is going to be mispointed. So what we've come up with is a sequence of procedures where we measure the starlight with the distorted deployed image. We analyze that starlight to find out where the errors are, and then we move each of those individual mirrors such that we fix it. The interesting thing is that process called wavefront sensing and control, part of that process was developed and perfected to fix the Hubble, which is kind of neat, because with all the bad press we got from Hubble, the techniques we used to fix it are now the techniques that are enabling us to go beyond. And then there's testing this thing. It's going to be big. It's going to be the size of a tennis court, and it's got to work at cryogenic temperatures. Now, the way you would test a normal satellite, you'd build it, you'd put the entire satellite into a big thermal vac chamber, and you would test its performance after it's all built. We cannot do that on James Webb. There are no chambers big enough to do that. So we have to build it up incrementally, and here's how we're going to do it. The ISIM, the science instruments, which will be done this year, will be assembled and put together in a structure down at the Goddard Space Flight Center. That should be done in 2014. We're going to actually be assembling the telescope at Goddard. We'll put the telescope together at Goddard. We will mount it or mate the science instruments to the telescope. Then we're going to have to send the telescope and the instruments down to the Johnson Space Flight Center to test at a large thermal vac chamber there, and I'll talk more about that in a second. Meanwhile, out at Northrop Grumman in California, the spacecraft and the sun shield are going to be put together. After this test, the space vehicle and the sun shield and the telescope and the instruments are mounted together and shipped down to the launch center in French Guiana. Now, this is where we're going to test, or what we're going to test down at Johnson. The telescope and the science instruments are going to be kind of mounted on the floor looking up. We're going to have test sources at the top of this chamber, and the entire chamber, everything in here, will be cooled to a temperature of around 50 degrees Kelvin. It is the largest cryogenic thermal vac chamber right now. And to give you a sense of how large it is, from there to there is about 5 stories. And here's a picture of it to give that picture scale. There's the individuals, and this is the cranes that are being used to modify that chamber. By the way, this is the same chamber where the lunar module was tested. For those that have gone to the movies, I guess it's also the same chamber where they filmed Transformers 3. And some of us, at least at NASA, were there when they were filming it, hoping to get in the movie, and I kept trying to weasel my way into telling the director, hey, when I describe James Webb to the small children, I describe it as a transformer because of the way it's popping out and doing all these deployments. I was hoping to get a spot, but it didn't work. Well, where are we right now in building this telescope? As it turns out, most of the stuff that required the most time is behind us. All the optics, 100% of the optics are done, and they work to within their spec. All the mirror segments are done. The secondary, the tertiary, all those mirrors, finished. The structure that holds all those mirrors together is being built in Utah by a company called ATK, and that's about 75% done. There it is there. The structure that holds all the instruments has been built at Goddard Space Flight Center, and it's done. Technically, we say it's 90% done. We're still touching up some things. The 4 science instruments are going to be delivered at the end of this year, at the end of 2012. One of them, the MIRI instrument, being built by Europe, has just finished its testing. I've been just out in Amsterdam to see the results of that testing. NIRSpec, which is also being built by Europe, by the European Space Agency, will be done later this year, as will the NIRCam, which is being built by the University of Arizona here in the US. And the Fine Guidance Sensor will be done in April. That's being built by the Canadian Space Agency. And finally, there's one of the sun shield membranes. The sun shield is about 40% done. The part that's lagging behind, and NASA did this by choice, the spacecraft bus is the last thing that will be built. The reason for that is it is the least risky. We've been building these type of things for almost 4 decades now. Let me show you what happens, and if you could click this for a second. Before you click it, let me describe what you're about to see. You're going to take a perfectly good mirror segment. It has been polished to 20 nanometers. 20 nanometers of perfection is sitting there. And after the opticians are saying it's perfect, here you go, guess what we do with it? Hit it. This is a vibration test to make sure that it can survive launch. Every optical engineer is starting to cringe right about now. Try to think of your $400 Minolta camera, giving it to me and having me do this to it. Right about now, that mirror is experiencing 9 times the force of gravity. It's being shaken right about now at 50 times per second. We'll go up to 100 times per second, 100 hertz. This was an engineering model of the mirror. I'm happy to say it survived. Everything went well. But I do often get a kick out of people who wonder why space equipment is so expensive. It's so expensive because after you make these perfect pieces of equipment, you put it in outer space by bolting it to some plastic explosive, lighting that plastic explosive, and the explosion follows you for the next 8 minutes into outer space, shaking you like that. And with the exception of things like Hubble, you don't get to fix it. It has to work right the first time. Summary. Telescopes then and now. Back when I was a teenager, when I was a senior and junior in high school, the largest telescope was Mount Palomar, located in the hills of San Diego, California, 5.1 meters. It's approximately 17 meters long, and it weighs 545 tons, or 495,000 kilograms. 41 years later, here I am. I'm on a team that's building a telescope just as big as Mount Palomar. Those two are to the same scale, those pictures. It's not going to be located in San Diego. It's going to be located 1.5 million kilometers from the Earth, beyond the moon. Its primary mirror will be bigger than Palomar. It'll weigh only 1/100th of Palomar, 6,500 kilograms. So, the future. And this deals with you more than me. For astronomy, investigation of dark matter and dark energy holds the promise, or holds the possibility, of some fundamental breakthroughs in physics. You know, if you look at the history of science, every time something big like this happens, you're on the threshold of a major, major breakthrough. That will be your generation. Observations of the early universe will reveal how the first galaxies and stars were formed. It's going to be up to you guys to figure out how you can form stars when there was no dust. Observations of exoplanets hold the promise of answering one of the most fundamental questions we have. Are there other Earths out there, and is there other life? You're going to be observing other worlds of our own solar system to help answer the questions of how the Earth will evolve. when you're a scientist and you want to see how something could happen, you take a sample space. You look at, if you want to know how this bug behaves, you look at other bugs. If you want to know how our planet will behave, look at other planets. Well, you have over 178 other planets to look at now. And for those of you that aren't going to become scientists but are going to become engineers, well, you'll be the ones who'll design the successor to the James Webb telescopes, and you'll look at telescopes to explore those parts of the spectrum we haven't seen yet. One of the ones that have always intrigued me are long radio waves. You'll learn how to build these telescopes in a more cost-constrained environment. Unfortunately for me, and even more so for you, you're going to have to learn to make these breakthroughs on very constrained budgets, but there are ways of doing that. You'll have to make trade-offs between whether it's better to do it on the ground or space. And if you are going to go into space, you'll probably be very interested in using robotic servicing to maybe fix the telescopes that don't work out quite the way you'd want them to. Finally, we've seen more progress in astronomy in the past 36 years than in the past 150, maybe 200. I'm not a real great historian, but I'd make this argument. You will be the generation of scientists that will use the James Webb Space Telescope. You'll be the generation of engineers that will design the next space telescope. Think of the possibilities and what one of you may be saying to high school students 36 years from now. Thank you, good luck, and have fun with it.